Welcome to my class 12 Physics, first chapter, that is electric charges and fields. And main point of discussion today, that is the third application of Gauss law. And what is that? That is electric field due to uniformly charged thin spherical cell. Thin spherical cell means its thickness is very small, just like this. This is the outer surface. This is the outer surface of a hollow sphere, and this is the inner surface of the hollow sphere, and this is the region. This is the region between the outer surface and inner surface, and this region is known as the spherical cell, and its thickness is very small, so that is known as the thin spherical cell. Clear? And this point is the center of the thin spherical cell, and here we take a point, first point, that is the outside the cell, second point on the thin spherical cell, and third point inside the cell, and at all points we will calculate the magnitude and direction of the electric field. Clear? And the first one, that is the outside the thin spherical cell. Outside the thin spherical cell. And you take a thin spherical cell. Suppose this one is the inner surface of the thin spherical cell, and this one is the outer surface of the thin spherical cell, suppose. And the thin spherical cell is positively charged. This is a positively charged thin spherical cell, and all the positive charge are closely packed. That means gap between the two positively charged is very small, approximately 0. So that this is the case of a continuous charge distribution. And you know, three types of continuous charge distributions are there. One is your linear or line charge distribution. Second one is your surface charge distribution. This is the case of surface charge distribution. And third one is your volume charge distribution. And suppose your total charge distributed uniformly, suppose Q. Then what is the surface charge density? In this case, we write, for surface charge density, symbol is sigma. Sigma is equal to, we write, surface charge density. That implies, you know the meaning of surface charge density, that is total charge. Suppose the total charge is Q divided by surface area. Surface area is S. That means if we take a unit surface area, number of charge present on that unit surface area is known as the surface charge density. And here if we take, suppose S is equal to 1, then Q is known as the surface charge density. Clear? And that implies sigma is equal to Q divided by, what is S? S is the surface area, and in this case, suppose this point is the center of the thin spherical cell, and this is the radius of the thin spherical cell. We write that is R, and the thickness of the thin spherical cell is very small. So that outer radius is equal to inner radius, both are approximately same. Then its surface area, you know the surface area of a sphere, that is 4 pi r square, and the radius is capital R. So that in place of S, we write 4 pi r square. That implies total charge Q is equal to, we take 4 pi r square to the left hand side, this is 4 pi capital R square multiplied by surface charge density. This is the total charge. This is the total charge uniformly distributed throughout the surface. Clear? And here, suppose this is the observation point. Observation point, we write that point, suppose P point, and at point P we will calculate the magnitude and direction of electric field, and for that first we draw a Gaussian surface. Gaussian surface means that is a closed surface. That may be a spherical surface, may be a cylindrical surface, or may be a cubical surface, but that is closed one. Clear? Not open. And suppose this one is your Gaussian surface. We draw a Gaussian surface here, passing through this point. Passing through the point P. And suppose this one is your Gaussian surface. And this is the observation point. And what is the distance? Distance of the Gaussian surface from the center of the thin spherical shell. We join from center of the thin spherical shell up to the observation point, and suppose this distance is equal to r. And here r is also the radius of the Gaussian surface, because a Gaussian surface looks like a spherical surface. Here Gaussian surface looks like a spherical surface, so that r is the radius of the Gaussian surface in this case. Clear? Then at point P, what is the direction of electric field? You know, direction of electric field is always outward. Direction of electric field is always outward from a positive charge. So that this is the direction of electric field, outward from the positive charge. And in this case, this is the radius. This is the radius of the Gaussian surface. And here direction of electric field is radially outward. Clear? And we take a small surface area, very small surface area. Suppose we write that is ds, and surface area is a scalar quantity. Then what is the surface area vector? You know, surface area vector is perpendicular or normal to the surface area. This one is the surface area vector, this one is the area vector, and here also we draw the area vector. This is the area vector. We write that is ds vector. That means ds vector is perpendicular to the surface area. This is the angle perpendicular to the surface area. Clear? Then what is the angle? Angle between direction of electric field and direction of area vector. In this case, both are parallel. Both are parallel means we write theta is equal to 0 degree. Clear? Now we applied Gauss law for this Gaussian surface, and we know from Gauss law phi is the flux, that is the electric flux, is equal to, what is phi? That is integration over a closed surface vector E dot ds vector is equal to total charge inside the Gaussian surface, not outside, divided by epsilon 0. That implies integration over the closed surface. This is A vector dot B vector, and you know in class 11 A vector dot B vector is equal to AB cos theta. You know this formula. So that here also we write that is E ds cos theta. Theta is the angle between electric field vector and area vector, and that angle is equal to theta, and that is 0 degree in this case. So that we write cos 0 degree is equal to q divided by epsilon 0. That implies we take electric field outside of the integration, E integration over a closed surface of ds cos 0, you know that is 1, is equal to q divided by epsilon 0. That implies integration of ds, that is we write s is equal to q divided by epsilon 0. That implies E multiplied by S. S is the total surface area, and here this is the Gaussian surface. This is the surface area of the Gaussian surface, not the thin spherical shell. So that S is equal to, here this is the Gaussian surface, and radius of the Gaussian surface is equal to r, and surface area is equal to, write 4 pi r square is equal to q divided by epsilon 0. Clear? Then what is E? Electric field. We take 4 pi r square to the right hand side, and finally we write electric field E is equal to 1 divided by 4 pi r square q divided by epsilon 0. That implies E is equal to, we write 1 divided by 4 pi epsilon 0 multiplied by q divided by r square. This is the magnitude of electric field. This is the magnitude of the electric field outside the thin spherical shell, outside the positively charged thin spherical shell. Clear? And what is the direction? Direction of electric field. Suppose thin spherical shell is positively charged. If thin spherical shell is positively charged, direction of electric field at point P is radially outward. And if thin spherical shell is negatively charged, direction of electric field at point P is inward and along the radius vector. Clear? Then that implies we also write electric field E is equal to 1 divided by 4 pi epsilon 0 multiplied by, what is Q? Q is the total charge, and in this case total charge, that is 4 pi r square multiplied by surface charge density. We write 4 pi r square multiplied by surface charge density divided by small r square. That implies electric field at the observation point outside the thin spherical shell. 4 pi cancel, remaining is equal to sigma divided by epsilon 0 capital R square divided by small r square. This is another expression for electric field outside the thin spherical shell. Clear? And second case, suppose on the thin spherical shell, means we take observation point at this point. This is the case of on the thin spherical shell, and at this point, what is the value? What is the magnitude of distance between center of thin spherical shell and the observation point? You know that is always r, and this is the small r. If point situated on the thin spherical shell, this is the distance, this is small r, and this is same as the radius of the thin spherical shell. So that on the thin spherical shell, small r is equal to capital R. We write second case. Number B, observation point situated is on the thin spherical shell. Clear? and on the thin spherical shell small r is equal to capital R. Small r means this is the distance between center of thin spherical shell and observation point. And capital R, that is the radius. And if small r is equal to capital R, then equation 1 becomes, this one is the equation 1. Here in place of small r, we write capital R, so that the equation becomes, we write simply electric field on the surface of the thin spherical shell is equal to 1 by 4 pi epsilon 0 q divided by, in place of small r we write capital R square. This is the first expression, and this is on the thin spherical shell. Clear? Similarly, another expression is that second expression, this one. Here also in place of small r we write capital R, then the expression becomes, we write E is equal to sigma divided by epsilon 0, sigma by epsilon 0, capital R square divided by, in place of small r square we also write capital R square. Capital R square cancel with each other. That implies finally we get E is equal to sigma by epsilon 0. This is the second expression of electric field, of magnitude of the electric field on the surface of thin spherical shell. Clear? Now, third case. Inside the thin spherical shell, observation point situated inside the thin spherical shell, then suppose this one is the outer surface of the thin spherical shell, and another surface is there. This one is the inner surface of the thin spherical shell, and this is a thin spherical shell, and the total shell or the thin spherical shell is positively charged, just like this. This is a positively charged thin spherical shell. Clear? And here observation point is situated inside the thin spherical shell, and this point is the center. For center we write O, and this one is the radius, you know that, and for radius we write capital R. Suppose this is the observation point. For observation point we write, suppose that is P point, and at point P we will calculate the magnitude of the electric field, and first we draw a Gaussian surface, and the Gaussian surface is also passing through the observation point, and this one is the Gaussian surface, and Gaussian surface is passing through the observation point. Clear? And this is the distance. This is the distance between center of thin spherical shell and the observation point. We write that is R. And look at the figure. Look at the figure. Here, inside the Gaussian surface, total charge is 0. No charge particles are there. So that inside the Gaussian surface, we write here simply Q is equal to 0, net charge is 0 inside the Gaussian surface, and we apply the Gauss law. Gauss law is integration over a closed surface vector E dot ds vector, this is the electric flux, is equal to Q divided by epsilon 0, and in this case net charge inside the Gaussian surface, that is 0. So that we write integration over a closed surface S vector E dot ds vector is equal to 0 by something, that is 0. That implies net electric field is 0 inside, this is the case of inside the thin spherical shell, clear? And this is all about your outside the thin spherical shell, on the thin spherical shell, and inside the thin spherical shell. Now we will draw a graph, that is variation of electric field with R. R means distance of the observation point from the center. And you know, first case, that is outside the thin spherical shell, and outside the thin spherical shell means small r is greater than radius of the thin spherical shell, clear? And in this case, what is the magnitude of electric field? Electric field E is equal to, this one is the expression, 1 by 4 pi epsilon 0 Q by R square. So that from this expression we get electric field is inversely proportional to square of the distance. We write E is inversely proportional to square of the distance. So that here we write E is inversely proportional to square of the distance of the observation point from the center of thin spherical shell. And in second case, on the thin spherical shell, and on the thin spherical shell means small r is equal to capital R, and in this case value of electric field is equal to this one. This is the magnitude of electric field on the thin spherical shell. We write that is 1 by 4 pi epsilon 0 Q divided by R square, and this is the maximum value. This is the maximum. Similarly, last one, inside the thin spherical shell, means this is the situation. That means small r is equal to 0 or greater than 0 but less than capital R. This is the small r, this is the capital R, this total, this is the radius of the thin spherical shell, and this is the distance between center of thin spherical shell and the observation point, that is small r. Here small r is less than radius and greater than 0. That means from 0 to capital R. We write here, this is the case of small r is in between center of the thin spherical shell and radius, clear? And in this case, what is the electric field? Electric field E is equal to, that is 0. We write that is 0. Clear? That means three situations are there. This one is the outside, this one is the on the thin spherical shell, this one is the inside. Clear? Then you draw a graph. Suppose this is the y-axis, one axis, and electric field is there on this axis, and another axis, second axis. Suppose this one is the x-axis, and we take r or distance. Clear? And here, this point is the origin. We write O, or that is the center of the thin spherical shell. Suppose at this point, this is the small r is equal to capital R, means this is on the surface, and this is the outside the surface. This is center of the thin spherical shell. This is the in between the center and surface of the thin spherical shell, means this is the case of inside. This point is the center. This is the case of inside the thin spherical shell. This point is the on the thin spherical shell, and this is the outside of the thin spherical shell. And suppose this is the value of electric field on the thin spherical shell, that is 1 divided by 4 pi epsilon 0 q divided by capital R square. Then inside the thin spherical shell, electric field is 0. No electric field is there up to R. That means up to this point, electric field is 0. This is one point. Then, when R is equal to capital R, small r is equal to capital R, this is the magnitude of the electric field. So that when R is equal to capital R, magnitude of the electric field is equal to this one. Here you draw perpendiculars, and both the perpendiculars meet at this point, so that this is the point. This is the point on the thin spherical shell, and then outside the thin spherical shell, E is inversely proportional to square of the distance. That means if we increase the distance, electric field is gradually decreased, and this one is the case. If we increase the distance, electric field is gradually decreased, and this is the E is inversely proportional to square of the distance, and this graph is for the outside, and this point is on the thin spherical shell, and this region is inside. That means your electric field is 0, and this is all about your third application of Gauss law. Clear? And thank you.